Okay, so good afternoon. Today, hopefully, I get a chance to finish the second lecture, the OS concepts. So we can start talking about concurrency from Tuesday. Okay, so we were talking about processes and specifically about multiprocessing or multi-programming. We said that there are two main components. The first one was scheduling, and the second one is protection. Now, this protection is needed for reliability, security, privacy, and also fairness. So when it comes to protection, we want to protect memory, we want to protect I/O devices, we want to protect the processor. The main tool in our arsenal to do protection is through address translation. And what do I mean by that? So far we kind of touched on the concept of virtual addresses and physical addresses. Now, it's the job of the operating system to map each process's virtual address space to physical memory. And this will be the topic of our discussion in the second half of the course. So here is the snippet of what it entails. Usually, we have segments of virtual address space. Like, for instance, here we have a segment here that is the code, a segment here that is data, a segment here that is heap, and another segment here that is a stack. And each process has its own segments. Like here, process 2 has its own segments. Now, the operating system, when it's running these processes, it maps each segment of each process's address space to a segment in physical memory, to a region in physical memory. In this example, you can see that the code from process 1 is mapped to this physical address range. One thing to note is usually virtual address space is sequential. So the addresses that you have are from 0, 0 to somewhere here 0xff, although there is a space here, as we saw, so they're not connected. However, when they're mapped to physical memory, they could each go to some arbitrary place in physical memory. So your addresses don't need necessarily to be sequential when they go to physical memory. For instance, you know, the address that the code 1 gets here is more than the address that data 1 gets here. These are physical addresses. Whereas in the virtual address space, the data had a higher range of virtual addresses compared to code. And that makes sense because, you know, it's a mapping. We don't need to make sure that the order is also the same. Now, one of the things that we talked about in inter-process communication was memory sharing. So with this model that you can see right now in front of you, I'm mapping each segment of each process to a separate physical memory region. And as such, these two processes have no way to modify, read, or write each other's data. So their data is completely isolated as long as I map them into different physical memory regions. Now, if you remember, one of the ways to do IPC, inter-process communication, was through shared memory. So if I were to implement shared memory, Unfortunately, I don't have a space here, so I'm going to just cross this over. Let's assume that this is an empty space. I can, and again, I don't have memory here. Let's say that process 2 asks operating system to give it a memory that it can share with process 1. So maybe operating system allocates some virtual address here and then maps it to this region. This could get an address, let's say 0x C something to 0x CF something, right? In virtual address space of process 2 and some physical address here, B, C, blah, 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 and then 0x, I don't know, B, let's not put 0 here, let's put it 0, and then F. But the point being, these two addresses don't necessarily need to be the same. Now, to share this with process 2, operating system might also allocate a region here, give it an address, which again doesn't necessarily need to be any of the two that we've seen. Let's say this becomes 0xa, 0 blah 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 to 0xaf, blah 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 blah, and then maps this region to the same physical memory. Now, what happened here is that each two processes now have a virtual address range that if they write to or read from, they're reading or writing to and from this physical memory region. They're not aware of this range. They don't care. They shouldn't care. They shouldn't know. So they just work with that region, right? And whenever they're working, reading or writing from their virtual address space, they're indeed sharing this physical memory region, and as such, they're sharing memory. So this is one of the ways that we kind of alluded to when we were, listing all the ways that processes can do inter-process communication. So this is one instance that you can just now see. Now, I'm not going to go deeper into this mapping and how we translate addresses. So we will spend a lot of time talking about this box here. It's not a box, it's oval, but we're going to talk about what is under the hood here. So what it takes to implement this translation map. So for that, just wait a little bit for the second half of the course, and we'll just talk about it. Okay, so I'm getting a question here. Does this potentially create inefficiencies if a process is given more space in regions than it needs? Do these regions dynamically change in size? This is a fantastic question. So basically, I talked about segments, and somebody is asking if these segments have fixed sizes, and I'm allocating them to you, but you only need a small fraction of it, what happens? And the answer is yes, this creates inefficiencies, and it's actually happening in our systems as well. The unit, if I want to be super formal and direct, the unit of allocation is not really segments in modern computers. It's called page. And pages have different sizes depending on architecture, depending on system, depending on operating systems. So usually there are a few kilobytes of size. So if you are allocated a page, but you don't need all of that, then that gets wasted, unfortunately. But having these units of allocations help in order to simplify the allocation. Where in your, I don't actually remember exactly. I don't think we have units of allocation in the labs. If I'm not mistaken, correct me if I'm wrong, but in the labs you can ask for any amount of memory you want. But yeah, so the unit of allocation in modern systems like Linux or others is pages, and pages have different sizes. Okay, we'll talk about that actually when we talk about address translation. Let's move on. Now I'm going to put everything together. So this is basically what we talked about. This is a Unix process. It has a sequence or a stream of instructions that has to be executed. It has some resources for it. Very specifically, it has a memory region. I have highlighted a stack here. It also has I/O state, meaning like what files have this has this process opened, or what sockets, and so on and so forth. And it has a context, which basically is the state of CPU corresponding to this process. What is the PC pointing to? What is a stack pointing to? What do registers contain? What values do registers hold? Now, very primitive computers had a single CPU, as you can see. And this is basically the early days of Unix. Each process had a single thread. So the way we can analyze this is each one of these processes gets to run on the CPU at any given time. Because of that, the switching overhead is high, right? Because we are switching between processes, and usually switching between processes means that you need to bring their memory bring their memory state to your physical memory, and copying memory state is absolutely expensive. Now, the process creation is expensive, since you want to set up the PCBs or TCBs. In this case, TCB and PCB are the same because each process has only one thread. Now you have to, let's say if you are forking, you need to make a copy of the parent's memory, and that's also expensive. So process creation is absolutely expensive. Now, when it comes to protection, we have a really good protection in this model because we are giving memory protection. We're implementing memory protection. So each process has its own memory region. And even if they want to talk to each other, it's going to be through operating systems. So memory protection, CPU protection are granted. Sharing overhead is high, as we discussed, because it requires operating system to get involved, set up files, or set up memory regions, or set up mailboxes for communication. So it involves operating system. It also involves context switching, right? If I have one CPU and process 1 wants to communicate with process 2, it not only needs to write its data, it not only needs to create this communication channel through OS. Whenever it writes, for process 2 to read, there has to be a context switch, right? So I have to now context switch between process 1 and 2 so that process 2 can read. So each sharing, each communication requires at least one context switch, which is costly. Now let's take a step further, add threads to this model, and see how those parameters change. Now switching overhead has gone from high to medium. The reason being that you might be switching between threads. And if you're switching between threads, so you still have one CPU. So at any given time, you're running one thread. But if the next thread that you want to run is from the same process than the current thread, then you don't need to copy everything. So your memory is not going to be copied because all the threads within the process share the same memory. So we're sometimes context switching between threads of the same process. Sometimes we're context switching between threads of different processes. So sometimes we are paying high cost. Sometimes we are paying low cost. So on average, we're paying medium cost when it comes to context switching overhead. Thread creation overhead is medium. The first thread that you create for your process is costly, right? But then the next threads that you're creating, the cost is relatively to what we saw in process creation is low. The same analysis that I did with the context switching, because you don't need to, for instance, set up the entire memory space. It's already there, so you can just create a new thread. Now, when it comes to protection, we have protection of the CPU that we get between user mode and kernel mode. But when it comes to memory I/O, memory and I/O, now protection has become no. The reason is I still have protection between processes, but between threads I have no protection. And we just talked about this in the previous lecture. We said that all the threads within the same process, they can actually see, read, write from each other's data, so the operating system doesn't provide any protection. And then the last one is sharing overhead, and it's lowish compared to what depending on what you want to do, but because threads within the same process can communicate with almost no overhead, then that's why we are saying that the sharing overhead is low. You still have high overhead if processes want to talk to each other. Now, take a step further, add not only adding threads, let's add more cores. Now, in this case, now the context switching overhead is actually low. The reason is because we have more CPUs. So it's possible, for example, to put each process on a different CPU. So when you're context switching between threads within the same process. So it's the context switching is always incurring low cost. Thread creation is low, protection as before, and sharing as before. One thing is that when you're sharing, it could well be the case that you don't even need to context switch, right? In this case, in the previous case, when you had one CPU, although your threads, share the memory, but they're still competing for the CPU. So if one thread wants to write something for another thread, at least we need to do one context switch between these two threads. Now, if you have multiple CPUs, you could potentially run one thread on one CPU, another thread on another CPU, and let them communicate. So conceptually, it's possible to do communication between threads without needing any context switching between them. To make this model even more advanced and closer to what we have in today's system, I got a question I will answer once I'm done with these. So just hold on to your question. I'll answer it. So I have to give you some introduction to go to the next level of making this model advanced, and that is hyperthreading. So let's talk about our instructions and the code that we're running. Let's say you have this code that has something like load some address to register 1, and then load some other address to register 2, and then maybe add register 1, register 2, and then write the result in register 3. Okay, so I have 3 instructions here. Instruction 1 and 2 are kind of independent, right? I can load address X to R1, and I can load address Y to R2. These are independent. But when it comes to the third instruction, there is dependency. It depends on both of the first 2 instructions. So I cannot execute the third instruction unless I'm done with loading X and Y to R1 and R2. Okay, with that in mind, let's talk about processors. So processors, the most primitive version is a version that can do one instruction at most at any single cycle. So that's the highest instruction per cycle you can get from this processor. So at any given cycle in your processor, so don't forget, like your processor has a frequency, so the clock ticks at every cycle, and at most you can do one instruction per cycle. Some instructions need more than one cycle. For example, load, right? If you have a load, you're going to go to memory, and we saw that memory is slower than your processor. So the frequency of your processor is higher than frequency of your memory. So that it takes time for you to load address X to R1. Now, this single instruction might take multiple cycles, right? But let's say you had both R1 and R2, and now you want to add them and put that result to R3. This is usually one cycle. So this takes one cycle to do. Now, as the Superscalar architecture allows us to do multiple instructions per cycle. Not only do one instruction, but multiple instructions. So the term that they use is they have multiple lanes. So in this figure that you can see, on the vertical axis, I have time in cycles. So this is cycle 1, this is cycle 2, this is cycle 3, this is cycle 4, and so on and so forth. So cycles are going. Now, each column is a lane. Basically, in this example, I can do 3 instructions every cycle. So my processor has 3 processing units in it. So like if you remember the picture I had, the ALU, you could imagine that you have like 3 ALUs. So you could potentially do 3 operations, 3 adds, let's say. You can do add 1, add 2, and add 3 in the same cycle. So this is the Superscalar architecture. Now, the colors here are each one of these field squares means that you're doing, in this example, you're executing an instruction. And empty cells mean that you're not using this resource because you can't. For example, let's say that I have 3 lanes, so I can do 3 operations per cycle. And let's say these are my 3 instructions. Now, although I have resources to execute them, because of the dependencies they have, I cannot really do the 3rd one. So I'm probably using 2 of them. And one of the units of operation that I have gets wasted. So it's an empty cell. And let's say this was a load, and let's say each load takes 2 cycles. So next cycle, I cannot do anything else. So for these 2 loads, I have to wait 2 cycles, let's say, for them to finish. Then I can go and do the rest of the operations that I can do, right? So as you can see in this model, there are a lot of empty cells usually. So these are wasted cycles that we could have done some operations, but we're not doing it because there is dependency between our threads, our instructions, excuse me. Now, what we can do to speed things up is to put 2 of these superscalars together in the same chip, which gives us a multiprocessor. And this way we can actually now start executing 2 threads instead of 1 thread. But we're still having these empty cells. We haven't solved that problem. One way to solve that problem is by fine-grained multithreading. What does fine-grained multithreading mean? It means that at every cycle, I'm going to switch in a fine-grained. This is done in hardware. So this is not done by the operating system. This is done in hardware. So at any given cycle, we're going to give all the resources in the processor to 1 thread. So in the first cycle, I'm going to execute instructions from thread 1. In the second cycle, I'm going to execute instructions from thread 2, and so on and so forth. And why is this good? Because if you remember here, from thread 1, there was this cycle 2 that was completely wasted. We were just not doing anything. We were waiting. Now, instead of waiting, I can execute thread 2's instructions. So this improves the utilization of my CPU. As you can see, there are less empty cells, but it still doesn't solve it completely. I still have these cycles that something like this, I cannot execute this add. Still, I can't execute it. So what should I do? This is where HyperThreading comes to rescue. So HyperThreading says, instead of not context switching, but switching between threads at every cycle, at each cycle, you should be able to execute instructions from 2 threads or 3 threads or 4 threads. Although I have to say, like, if you have bought processors, you know that the highest that the industry has adapted this is 2 threads. So when you buy a processor, it has 1 physical CPU and it tells you that it has 2 virtual CPUs, and that's pretty much it. So now in this model, I don't need to wait here not doing anything. I can schedule an instruction from thread 1 here, and then next cycle I have all the resources given to thread 2. Next cycle I can execute again this empty cell that I had here. I can now execute something from thread 2. Now this gives us the highest utilization possible. But you might ask, okay, so is there any free lunch? And the answer is no. There is a trade-off between performance and utilization. So we can compare this with this one. So we can compare this simultaneous multi-threading, compare that with having 2 CPUs. So the utilization when you have 2 CPUs is lower. You have a lot of empty cells, but the performance is higher, right? Because there is no competition between these 2 threads for resources, right? It could well be the case that both of the threads have instructions to execute, but the hardware has to choose which thread is going to run at this cycle. In the multiprocessor setting, you don't have that competition. Each thread gets its own resources, so there is no competition. So performance is better when you have multiple cores. Comparing, for instance, 2 physical cores, compare that to 2 virtual cores. Well, 2 physical cores gives you the highest performance, but the downside is utilization. 2 virtual cores give you higher utilization. The downside is performance. So you're paying performance for utilization, or you're paying utilization for performance. Now, this is where I'm going to actually end. There are much more to say, how hardware decides what to run, what not to, what kind of resources the hardware needs to provide. I mean, it's very at the surface of it, you know, the hardware has to have 2 program counters at any given time in order for it to be able to execute instructions from 2 threads. You need 2 PCs. You probably need to share registers, right? You probably need to have bigger resources inside your CPU to be able to implement simultaneous multi-threading. But usually you don't double everything. You just double necessary things and let threads share the rest of them. And that's where that, if you were to just double everything, then you're basically doing the multiprocessor. So you're not doubling everything, but you're doubling some stuff like PC, for example, or stack pointer. But that's it, right? The rest of the resources are shared, and that's where the competition comes in. If you're interested, definitely take a look at this link, and you can just search internet and find a lot of information on this. Now, I'm getting questions and I'm aware of them, and I'll answer them once I'm done with this, put it together kind of run that we're doing. So let's now take that a step now that we have the introduction. In this last one, not only I have multiple threads, not only I have multiple CPUs, but I also have these virtual CPUs. So I'm basically doubling the kind of, not exactly doubling, but I'm providing more resources to be able to run 2 threads at a time. Now, if you look at this one, this model, well, what happened. So switching overhead is really low. If you talk about the two threads that are running in the hardware, the switching overhead is almost zero because it's done by the hardware. Hardware is doing the switching. But even if you talk about threads at operating system level, the mere fact that we have more CPUs, so more computing resources, it means that we basically need less context switching. And because we need less context switching, the cost of context switching gets amortized and goes down. Now, again, as I'm just repeating myself, the only downside of this last model is basically these shared resources. So now we're sharing hardware resources between threads, and that could hurt performance. So for those of us who are working like in data center, research, we usually have to make this decision. Do we want to enable the hyperthreading capability of our CPUs, or do we want to just disable it? When you enable it, from the operating system's point of view, it's as if you have two CPUs. In reality, you don't really have two CPUs. Hardware is kind of like emulating it, but operating system doesn't care if the hyperthreading is available. Operating system schedules two threads, right? And if you disable it, then operating system says, oh, there's only one core here, so I'm going to just schedule one thread, and that gives better performance but lower utilization, as we discussed. So this is a trade-off you have to make sure you think about when you're designing your system, you're setting up your system. Okay, I think this is a good place to answer some of the questions that I got. Okay, so the first question, back in 2015, I had this game cheat engine that could analyze the memory of other processes and change values in that memory to cheat in single-player games. How could this happen with OS level protection? So if I were to guess, is that this game engine that you have, each player gets its own thread, not their own processes. So all of these are sharing a state, and that's why your engine is able to change stuff. If there were different processes, then you can't, unless there is, for example, so there are these cases where like you might have different processes, but they're all reading from the same file, right? So if all of them are reading their data from the same file to say who has how much it scores and so on and so forth, and you can access that file and change that file, then, well, everybody is reading from that file, right? So then you're able to change everybody. So from the operating system point of view, operating system says, okay, you asked for sharing and I'm providing sharing. I don't care if one of you is malicious. You should think about this between yourselves, right? So that's that. I hope I answered that question. So it's either multi-threading, or if it is multi-processing, they're sharing data either from a file or from a memory region. And that's how one of them can go and mess up others, if one of them is malicious. Okay, so another question here is, so in fine-grained multi-threading, is it always going back and forth each cycle between two threads, or is it this example? This is one example, right? So it could be every 2 cycles you context switch, or every 3 cycles you context switch. Sorry, not context switch. You switch between threads. This is just an example. And also the order. This is a lot of hardware architects talk about how to basically make a decision who gets what resources. So they might implement their own hardware scheduling, which is different from operating system scheduling, right? Okay, how does pipelining in processors interact with hyperthreading? Not much. Unfortunately, I can't talk about this now. By by training, I'm also a computer architect, but that would require another, lecture to talk about, pipelining and hyperthreading and how they interact and stuff like that. So I'm going to leave that to, if you're interested in these topics, you can take a, computer architecture course, advanced one here at Waterloo, or maybe, watch online lectures that are available if you wish to know more about this. So sorry about that. Okay, can we have multi-processor architecture and simultaneous multi-threading at the same time? Yeah, I mean, it was in the last figure. Can you explain the lanes in more details? I think all you need to know is just the high level, right? So in a usual CPU, you have a single ALU, for example. So 2 registers come, and then another register has to get a value. So if you have multiple lanes, then you have multiple of these ALUs, right? So you can do, for instance, in this example, you can do 2 arithmetic operations at the same cycle because you have 2 ALUs. Usually systems have 1 ALU for integers, 1 ALU for floating, and basically double precision arithmetic. So you could have different kind of execution engines inside your processor, and that allows you to do more than 1 instruction per cycle. I think that's all you need to know. I mean, obviously there are much more to know about that, but for the purpose of you understanding what I just said, that's enough. Okay, so let's move on to the 4th operating system concept called dual mode operation. Now, the operating system code, the kernel code, we want it to be able to do anything it wants. We want it to touch any physical memory it wants. We want it to be able to disable, enable interrupts. We want it to set up, vector, as we will talk about, the page tables, all sorts of things that the hardware wants. So kernel code should be able to do whatever ISI permits. Now, we don't want to give all that power to a user mode program, right? Here is an example. Let's say I have this user code. I think I gave this example before, but let's say this is my user that does this while true. And that's it. So as you can see, this process is not just doing instructions, right? Now, if operating system jumps to this guy, the only way that operating system has to take control back from this guy is to preempt it, to somehow force this to stop and get control back. Now, one of the ways that we'll see that operating system can do this is through interrupts. For example, the operating system can set timer to some time, let's say 50 microsecond. So, hardware, different processors have different number of timers. A timer is a register that counts down, and once it gets to 0, for example, or maybe it counts up, when it gets to FFFFF, basically the maximum number, it raises an interrupt. You can configure a timer to raise an interrupt, and maybe operating system does that. So it says, okay, timer, I'm setting you to 50 microsecond. When you get to 0, so count down, and once you get to 0, raise an interrupt. And when an interrupt happens, then hardware switches to kernel and takes care of what should be done. Now, if my user program is able to disable interrupt, why it's not? Oh my God! The pen ran out of the battery. So sorry. I should have charged it. Okay, so if my user program is able to disable interrupts, then the operating system can never get control back. So then the user goes there and continues running forever, and that's it. The other example is if the user program can access anywhere it wants in memory, then we're screwed. The user can go and mess up the kernel memory, right? So what we're going to do is we want the hardware to provide us with at least 2 modes of operation. So in one mode, which you could call supervised mode or protected mode, the code that runs in that mode can do anything it wants. And now this is where kernel comes in. What is a kernel? Kernel is any code that runs in this mode. So any code that runs at supervised or protected mode or kernel mode, we call it a kernel. And the other mode that we want some protection, some limitations, we're going to call it user mode. So in user mode, there are some operations that are not permitted. And this is necessary, right? To do what we want to do in operating system, to implement what we need, what we want in operating system. Now, this is one of the areas that you should ask me, is this necessary, meaning that we can't have an operating system if we don't have 2 modes? Is this like very necessary in a sense that if we don't have it, then we can't have operating system? And the answer is no. Let's say we only have 1 mode. Then we still can have operating systems. We can run our operating system in that mode, and the operating system can then interpret, for example, the user code. So operating system then, reads user code and then deciphers the code and then decides if the instruction that this user wants to do is permitted or not. But as you can see, this is going to be extremely expensive, right? It's kind of like operating system acting as an interpreter for user code. And we definitely don't want to do that because it has a performance cost. So having dual mode provided to us by hardware makes our life easier and gives us performance. So this is another, like, if you remember, I talked about this lecture 1, that we're going to rely on hardware, but this reliance is kind of to get performance. We still conceptually can do many things by ourselves. Okay, so what do we need for, what are the requirements for the hardware to provide this? The minimum of it is a single bit somewhere in hardware, a single bit. For example, if you only have 2 modes, you need only a single bit. In x86, you have, I think, 3 or 4 modes. In ARM, you have up to 7 modes or 8 modes. So this is at least. How much charge does this guy have now after a few minutes? Oh, that was good. Okay, so at least 2 modes, right? It could have more. So if you go with 2 modes, then you only need a single bit to basically know which mode you are. Now, the other thing that we want the hardware to do for us is to go from kernel mode to user mode. We want hardware to do some stuff for us. And going from user mode to kernel mode, we again want hardware to do some stuff for us. Kind of like hardware has to also provide instructions to change the mode, has to provide instructions to return, for example, to user code, to user mode from kernel mode, or go from user mode to kernel mode. So these are the things that we want hardware to provide for us. Now, there are three types of mode transfers. Basically, three events cause a mode transfer. And here we're talking about user mode to kernel mode. The first one is system call. So when a user program, user code, which by that we mean a code that is running in user mode, calls into operating system for a service, like open this file for me, or write to this file, or close this file, or delete this file, or open this socket, right? So these things, they internally execute an instruction that is called trap or system call. It has different names in different architectures. When that instruction is executed, the mode transfers from user to kernel. The second one is called processor exceptions. Processor exceptions are internal and synchronous events that are caused by the code, by the user code. For example, if your code divides by 0, or if your code accesses a memory that it's not supposed to access, and that would cause a segmentation fault or a page fault. So this is basically internal to your code. Your code caused this, and that's why we call it processor exceptions. Now, there are asynchronous events that could happen, and we call those interrupts. Usually, if you read texts, sometimes these two, both of them are called interrupts, or both of them are called exceptions. The reason I'm making them two separate entities is because one of them is synchronous, one of them is asynchronous. The interrupts are not related to your code, right? For instance, the timer interrupt that I talked, operating system sets that timer. You start your code. Somewhere in your code, this interrupt happens, and it has nothing to do with your code. Or for example, your code is running and a packet comes from network, and that causes interrupt. Or for example, you read a file and the SSD finishes bringing the file and it raises an interrupt. So these are external to your program. Now, to implement, I told you that we kind of want hardware to implement this mode transfer or give us some support for this. We have three requirements for the hardware to do. The first one is we don't want the hardware to allow user to be able to jump anywhere it wants in the kernel code, right? We're going from user mode to kernel mode. We want the entry point to be well-defined and protected. So we want limited entry points to kernel. Otherwise, for example, if your code can call open a file and it's able to jump somewhere in between the open code in kernel, it could open something that it's not supposed to open, for example. Now, the second thing is we want atomic change to processor state. Now, what do I mean by atomic? Atomic basically means either all or none. So that's atomic. Now, what do we mean by atomic change in processor state? So we talked about this single bit that is, when it's 0, it's user mode. When it's 1, it's kernel mode. So changing this bit is one operation that is corresponding to this mode transfer. But other than that, we need more things. For example, we were running user code. Now we want to run kernel code. So PC should also change. So PC was pointing to user code. Now I want PC to point to kernel code. So this is the second operation. The third one is kind of a stack. So a stack pointer was pointing to the stack of the user. Now I do a mode transfer. I want the stack pointer to point to the kernel stack. So these are different operations. Now I want them to be done atomically. I don't want to change mode and the process state hasn't changed. Like PC is still pointing to the user code. That's dangerous, right? Because now I can run the user code in kernel mode. So I want all of these to happen at the same time, or none of them to happen. Now, the third requirement that we have is transparent and restartable execution. So what do we mean? We mean that when you're writing your code as a programmer, you never think about what's going to happen if at line 20 of my code an interrupt happens. You don't really care, and it should be transparent to you. You should be oblivious to it. So operating system and hardware together have to make sure that when an interrupt happens, when a system call happens, when an exception happens, we can reserve the state of the process, go handle that event, and then come back to that code and restart it without changing the state of the process, so that everything was transparent to the user code. Now, let's start with the first one, which is the, okay, I got a question. Why is kernel code called kernel? Precisely because it's running under kernel mode, right, as I described. Now, let's go to the first one, a well-defined protected entry to the user to the kernel code. Now, for that, different architectures provide interrupt vector table. What is an interrupt vector table? This basically is a region of memory that hardware has designated for interrupt vector table. So if you ask me what it is, it's just a region of memory, right? And hardware says, when a certain event happens, I am going to go and check this region of memory. And this is, well, this is a interface that hardware provides. Now, operating system's job is to know this, that, okay, there is this region of memory that hardware is going to go look when certain events happen. I have to tell hardware what to do when that event happens. So hardware, for example, in x86, in the first 32 entries are dedicated to exceptions. For example, divide by 0. Now, if a divide by 0 happens, hardware is going to go and check this specific memory region or this specific memory address. Operating system at boot up writes the address of handler for divide by 0 here. So it's kind of like a level of indirection. When hardware is when the operating system is booting up, it knows this address is going to be used for divide by 0. Whenever divide by 0 happens, hardware is going to come and check this. So I better write the address of divide by 0 handler here. Now, during the runtime, if divide by 0 happens, hardware comes, checks this memory location, and finds the address that operating system wrote, and it just jumps there. So it jumps to that address, and that's how you can handle divide by 0. There are, in x86, for example, entries for different interrupts, like timer interrupt gets its own, and so on and so forth. So each kind of interrupt that you might have in your system gets its own entry. And then, so we covered exceptions, we covered interrupts. Now there is a single entry, at least in x86, for system calls. So every time your code executes trap, this trap is like an instruction. I believe in ARM is SVC. So whenever you call SVC, your hardware is going to go and look at this region, this byte, and find out where the handler is. Now, inside this handler, you can then decide where to go, right? If it is an open, if this system call was an open a file, then you handle opening a file. If this system call was writing to the file, you will handle that. If it's opening a socket, you go and open a socket. But all your system calls have the same entry point. So whenever this trap or SVC is called, usually you pass a number like SVC, let's say 10, and then you associate 10 to certain things. So maybe 10 is to open a file, and 11 is to close a file, and 12 is to delete a file, and so on and so forth, right? So that's that. So this is interrupt vector table. So operating system with cooperating with the hardware can make sure that the entry point to kernel code is well defined and protected. So as long as the operating system writes this handle divide by 0 or handle system call or handle timer interrupt in a correct way, then hardware makes sure that it's going to jump to the beginning of that code. Okay, now let's talk about kernel stack. We talked about this concept of being able to restart the program from where it was interrupted or preempted. So to do that, we need to save the state of the current thread or current process. We have to save it somewhere. Where should we save it? One first thing that might come to your mind, okay, maybe we save it somewhere in user memory, right? And in particular, we might actually want to save that on user stack, right? Can we do that? Is that a safe option? The answer is no. You should never, under any circumstances, use user memory for your kernel code, because it's against reliability, it's against security. So don't forget that, let's say you have a multiprocessor, one thread of process 1 is running on core 1, and another thread of process 1 is running on core 2. Now, let's say thread 1 on core 1 is interrupted. If operating system uses the stack of this thread 1 to save its state, the thread 2 still has access to that. So thread 2 could go and mess it up, whatever operating system has saved. So it's against reliability, it's against security. Maybe operating system, checks that the file that the thread wants to open is a safe file, and the process has proper access authorization to open that file. And right after the operating system checks that, and before it opens that file, another thread goes and changes that file to something that this process doesn't have authorization to open. And then operating system thinks that, okay, I have checked it and it was okay, so I'm going to go and open it. Now it has changed, right? So it's against security, it's against reliability. We should not trust user program. Now, okay, so what do we do? Well, we're going to designate a kernel thread, a kernel stack. Somebody's like, Lou, funny memes. Yeah, thank you. So the kernel is going to designate a space for this particular thing, and that we call kernel stack or kernel interrupt stack. So I think that the name is kernel interrupt stack. I'm just going to call it kernel stack. Now, some operating systems take another step, go a step further, and designate one kernel stack per thread. So each thread has its own kernel stack. So again, I repeat myself. The bare minimum is to have at least one kernel stack to use for all threads. But for simplicity, to make our life easier, many operating systems take a step further and allocate a single kernel stack per thread. So now each thread has its own kernel stack. Now, here is an example running this mode transfer. So at the beginning, I have the user stack empty, kernel stack empty, and as you can see, this user thread has its own designated kernel stack. Now, let's say I start, I do my main, so I push everything for main on my user stack, and let's say main calls procedure 1, procedure 1 calls procedure 2, procedure 2 at this point calls a system call, let's say open a file or something. So when it calls the open whatever and pushes the name of the file, whatever is needed for that system call is pushed on the user stack. And at this point, we're going to execute the trap. So the mode is going to change. The first thing we're going to do is to save the CPU state of this process or this thread. So where do we use to do this? We're going to use the kernel stack. So we use the kernel stack to take a copy of whatever is important to us that we want to come back to. Then we continue using this stack for whatever code that is going to be running to handle this event. If it is a system call in this example, or maybe it was an interrupt, or maybe it was an exception. So in the case of, let's say, like a system call to open a file, we're going to just run the system call handler. So now we're going to push everything related to this guy. And let's say at some point, this guy is going to call the driver, right? So we're going to use it for the driver code as well. So driver code usually, unfortunately, actually, in Linux, run in kernel mode because they have to talk to the hardware. But anyhow, it's unfortunate that we have third-party like NVIDIA writing hardware drivers that can run with full access to our system, and we have no idea what the code is. And that's sad. But anyhow, so your IO driver runs and it uses your kernel stack. And so let's say it's done. We pop all the things from the stack, and now we're ready to go back to our process. So this is the state of the kernel stack and the user stack when we're ready to go back. The moment we go back, we just read everything from kernel stack, put them on the CPU registers, and then we switch mode to user mode. I got a question. What exactly gets stored in kernel stack? If you're asking about this CPU user CPU state, just wait a little bit. I'll talk about what is exactly we need to say. If you're talking about it's not just the only thing that gets on the stack, as you might have noticed. We're using this kernel stack for whatever code that we're running in kernel mode to take care of this event that has happened. So the system call handler or the interrupt handler, and then the driver, whatever kernel code that we're going to use is going to use this kernel stack. Okay. Now, disabling interrupts is something that we talked about, and we want this to be a instruction that user program cannot execute, as I explained that in that example. When you disable interrupts, you're really not ignoring them. Sorry, you're not really disabling them, you're just ignoring them. So sorry, what that means is all the interrupts that come while the interrupt is disabled, they get queued. And the moment you enable interrupts again, you have a queue of interrupts that you have to then manage. The other thing with this queue is usually different interrupts have different numbers. So some interrupts have lower numbers, some interrupts have higher numbers, and some hardware they sort interrupts based on their number. So some interrupts get higher priority. So if you get 2 interrupts at the same time, let's say your timer interrupt goes off, and at the same time your SSD has finished bringing data to memory, and let's say a message has come to your NIC, a packet has arrived. Now each one of these interrupts get a number, but then they get sorted in the interrupt queue, and then you start with the highest priority interrupt to take care of. Now, one of the things that you have to pay attention to is when you're inside your interrupt handler, do you want, usually most architectures like x86, at the beginning they disable interrupts, but it's part of the atomic mode transfer. One of the things that happens is the hardware also disables interrupts when an interrupt happens or when a system call happens. Now, so you enter the kernel mode with interrupts being disabled. Now you have an option to enable interrupts if you want, and sometimes it's a good practice to do, but you have to also think about what it means to enable interrupts while you're taking care of one. There is a possibility that you get, it's kind of like a recursive call, function call, that you could potentially get a Stack Overflow. So if within your interrupt handler an interrupt happens, and within that interrupt handler another interrupt happens, and so on and so forth, you could start pushing stuff to the kernel stack, and then that could overflow. And if you remember, I told you that the kernel stacks are usually limited to 8 kilobytes, for example. Their size is limited. So for simplicity, at least in the code that you're going to work for your labs, we're disabling interrupts when we go to system mode, to supervised mode, and we keep them disabled during handling of that interrupt. Different operating systems do it differently, but the bare minimum is that you want to make it disabled for at least few instructions, and then you do some important stuff that you really don't want to get interrupted. And then once you feel like you could now be interrupted, then you enable interrupts. So here are examples from x86. These are the instructions to disable and enable interrupts. And these instructions, indeed, as I said, are only executable in kernel mode. You cannot execute them in user mode. Okay, these are the steps that are taken in an x86. I guess let's yeah. So the first thing these are the operations, and we want to do this atomically. So either all of them happen or none of them happen. So all these instructions that you see here are going to happen, or none of them is going to happen. So the first thing that the hardware does, it disables interrupts. It saves your, okay, this has to be PC, not PS. Your program counter, your stack pointer, and your exception flags are copied into a temporary hardware register. Then you're going to switch the stack pointer to point to the kernel stack. So you might ask, how does the hardware know which kernel stack to use? The answer is the operating system, when it schedules a process or a thread to run on CPU, before jumping to that thread to execute it, it tells the hardware that if any of these three events happen, exceptions, system calls, or interrupts, here is the address to kernel stack. Use this kernel stack if it happens. So hardware usually has a register that operating system tells the hardware, in case something like a mode transfer happens, use this stack pointer. So I think in the codes that in the boards that you're using, it's MSR and I think it's PSR. So one of them is MSR is the kernel stack pointer. It's a register for kernel stack. So the operating system sets this register right before going to jump to the kernel, to the user code, so that if anything happens, hardware knows where the stack pointer is. Okay, so here the hardware switches to that stack pointer and then pushes these three values into that stack pointer. Optionally, hardware could also save some error code. Let's say if it was an exception, you want to say which exception it was, or if it was an SVC, you want to say which SVC it was, 0, 2, 1, whatever. And then lastly, hardware is going to invoke the interrupt handler, basically make PC point to the handler. So all of these steps are going to happen atomically by the hardware. So let's look at them in some more details. So here I have there are multiple components in this figure. So let me explain one by one. So this is the code for kernel interrupt handler. This is the kernel stack that is empty at this point. This is the code that we're running right now, user level process. This is the user stack. And finally, this is the state of the processor. So we're showing you PC, SP, the E flags, and other registers, right? So that's the state of the process. Now, when we're running the process, when we're running this user mode process, PC is pointing to somewhere in foo function, let's say, right? And then the stack pointer is pointing to the top of the stack, user stack. So, and as you can see, on top of the stack, I have the foo, right? And I have a bunch of other things which I have pushed. Now, let's say interrupt happens. Immediately, hardware has done all the things that were in that picture in the previous slide. So let's look at it. So hardware has pushed stack pointer, has pushed PC, has pushed E flags, and in this example, the error messages, the error flags, sorry, the error registers to the stack. So all of them are pushed on the stack. A few points. So this SP is the previous SP, right, where we were running the user code. So this guy is pointing to the top of the user stack. As you can see, this guy is pointing to the user stack. And PC is the previous program counter, where we were in the program. So we were somewhere in the foo, so PC is pointing to foo. Now, the new stack pointer now is pointing to the top of the kernel stack. And the PC is pointing to the interrupt handler. So all the steps that I showed you in the previous slide happened atomically. So this is now the beginning of the handler. Now, if you remember, I told you that inside the handler, the first thing we do is we copy the state of the processor. Now, the hardware has helped us by making a copy of the a stack pointer of the user and also making a copy of PC. These are the things that we need the hardware to do for us. Now that we said we want double mode operation, we definitely need the hardware support in this part. This part operating system cannot do by itself. Why? Because if hardware doesn't copy the program counter of the user, now the new PC is pointing to kernel code. Kernel doesn't have any idea where the PC was before, right? So this is where we actually need the hardware support, and this is necessary, right? This is now that we said, okay, hardware, come and help us to get performance, give us dual mode operation, although we didn't necessarily need it. But now that we said, let's do dual mode operation, now this part, we actually need hardware support to take a copy of PC, for example. And the same with the stack pointer. If a stack pointer has changed, we don't know what the previous stack pointer was. In ARM, if I'm not mistaken, you have separate registers for PC. So you have a PC. No, actually, you have one PC, but the hardware saves PC in a register. It doesn't push it to a stack, if I'm not mistaken. And the same with the stack pointer. Again, if I'm not mistaken, the hardware saves the stack pointer in a register, right? In x86, hardware pushes them to a stack. In ARM, at least in A9, I'm not sure about M3. I think the board that you're running is M3. But in A9, which we're doing in EC350, in A9, hardware saves these in a register, right? And then the operating system can copy those registers, right? But the bottom line is hardware should save them somewhere. And then operating system, when it starts running, it can copy them, put them in the stack if it needs to. Now, in x86 again, usually the first thing that we do inside our handler, we run this push AD instruction. And what does this push AD does? Push AD basically pushes all the registers to the stack. So now a stack pointer is pointing to the kernel stack. If I execute push AD, I'm going to make a copy of all the registers. Now, you have to notice there are two SPs here. And I usually ask the students, are these two the same? And the answer is no, they're not. So this SP is a SP that the hardware copied for us, and it points to the user stack. This SP is the SP that was pushed because of this instruction, push AD, right? And when we executed push AD, a stack pointer was pointing to the beginning of the stack. So the stack pointer that we, this SP, this second SP, is pointing to kernel stack, somewhere in kernel stack, and this SP is pointing to the user stack. Now you might ask, okay, why are we making this copy? The answer is, well, it's like convenient to just call this push AD. Otherwise, you have to have a bunch of code push, AAX, EAX, EXP, blah 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 blah. You just execute this instruction, and it makes a copy of all your registers, and SP is included. In fact, when you want to pop them, there is an instruction pop AD, and this pop AD actually throws away SP. So it doesn't. It pops it from a stack and throws it away. It doesn't change the stack pointer after it pops it. Okay, so that's that. I only have 1 minute, so I'm gonna actually pause here. I was hoping that I can finish these slides, but unfortunately it didn't happen. Okay, dude, get out. Let me see where I am. Are you kidding me? Okay, discard. Okay, so almost there. Okay, so probably next lecture on Tuesday, we have to speed it up to finish it up and then start concurrency. So I have a bunch of questions here. Let me go through them. Is the kernel stack on top of the user stack? No, so the user stack is in user memory and kernel stack is somewhere else in kernel memory, right? And they could actually, in terms of their actual location in physical memory, they could be totally they could be on top of each other. They could be different. They're different entities, right? One is in user memory, one is in kernel memory, and wherever they are in kernel memory or user memory, they're going to be mapped to somewhere in physical memory, right? Okay, so that's that. Let's say you have a program that has two processes. You have a program that has two processes. What does that mean? You have a two-core machine as well. Now, one process runs into an interrupt. Would both processes be? I guess you mean you have two processes and then two processors, I assume. And then one process gets interrupted. Yeah, so interrupts are usually for each CPU. So if one CPU gets interrupted, the other CPU doesn't necessarily need to be interrupted. A CPU can interrupt another CPU, so it's called inter-processor interrupts. So one CPU can interrupt another CPU, and we will see a use case for this, why this is actually necessary. So do we see it actually in SE? Yes, we do see it in SE, yeah, definitely. So just wait for that. Yes, so I hope I answered that question. So anyhow, so when interrupts happen, it's just one CPU. It's like each CPU has its own interrupt system. Why do we do interrupt masking? I don't really understand what property this enforces. So as I said, if we will see actually how masking interrupts could come handy when we talk about synchronization and stuff. So wait a little bit for examples of interrupt masking. But the other example that I actually gave was, let's say, you keep getting interrupted, and each time you get interrupted, you're going to push stuff on the stack. So you might actually run out of a stack space, right? You might overflow. So you might say, one example, let's say you want to do a scheduling, right? During a scheduling, you don't want to be interrupted, because if you get interrupted, then if you were in the middle of changing the state of one thread from ready to blocked, or from ready to running, and you got interrupted in the middle of it, so you've done some of that work, because when you think about scheduling, you also want the scheduling to be atomic, right? You don't want to just change the state of a thread without actually setting up its state or whatever. So the scheduling also has a bunch of steps that you want to do atomically. Now, if you get interrupted in the middle of it, you might put your system in a bad state, in an undefined state. So that's another example that you want to disable interrupts so that you can just not get interrupted, go through the instructions that you want to do for anything atomic that the operating system has to do, operating system. We usually use this disabling and enabling interrupts. Okay, how do you define atomically? I kind of defined it, right? Atomically means either all of them are executed or none of them, right? You don't want, for example, to change the mode, but then PC is still pointing to user code. That's bad, right? You want mode to change and also PC to change and also a stack pointer to change, right? You don't want to be in the middle of these operations. You want all of them to be happening at the same time from the perspective of, let's say, the code that you're running. Would the interrupt stack be directly accessed on physical memory, or will it be on some separate virtual address space? That's a good question. Usually, even kernel has its own virtual address space. So kernel, for some stuff, uses virtual memory, right? So kernel has its own virtual memory, and there is a mapping from that to physical memory. Now, this could mean that there is overhead for this translation to happen. To reduce the overhead, at least in the past, after a security risk, this has changed and mitigated. But in few years ago, at least, usually kernel virtual address is mapped to all processes in Linux systems. So if you look at the range of virtual addresses in kernel, let me actually show you. If you search, for example, Linux virtual address space image, you can see that at top it's designated for Linux. So Linux maps its own virtual address to every process's virtual address. But then the programs, the processes don't have access to this region. So if they try to access those virtual addresses, although it's inside their own virtual address space, if they try to access anywhere in that, they get segmentation fault because they don't have access to that range, right? It's kind of like accessing in between the stack and heap that is not allocated to you. So anything that is not allocated to you, you get segmentation fault. So that's pretty much it. Yeah, as you can see, so you can look at these pictures. So usually kernel is mapped to the higher addresses of of processes. This changed. This paradigm dramatically changed after the meltdown attacks. So after Spectre and Meltdown, I think it was mostly Meltdown. This has changed. So the operating system, the Linux operating system, doesn't map its entire or part of its virtual address there. I think it has become very, very limited how much it's mapped to user space. If I have time, we'll see. In ECE 350, I talk about it. I don't know if I will get a chance to talk about it in SE 350. But if you're interested, you can look at Meltdown and Spectre security risks and to get more information on that. Okay, sorry, I again went over time. Thank you for those of you who stuck around. Thank you for those of you who attended the lectures, asked questions. I really appreciate it. I think it's very important that you guys come. I hope it continues. And thank you for those of you who are watching. If you're watching this, please come to the lectures. It's more fun when you guys ask questions. Take care, be safe. Talk to you on Tuesday. Bye-bye.